When you're working with programs that involve data, you often want to organize your data such that your items are sorted, least to greatest or greatest to least. For example, when you are interacting with an e-commerce website and you have some search results and you sort by price, you typically want that least to greatest, or by user rating from the best rated products to the worst rated products. We sort information in order to make the things that we're looking for easier to find. And there are many applications of sorting in computer programs. It's one of the oldest kinds of algorithms in our discipline. So what we're going to look at in this video are some of the built-in functions of Python that allow us to sort, say, lists of data. And then we'll take a brief look at one of the simpler kinds of sorting algorithms, an insertion sort algorithm. So let's jump right into a Python example. In this example, what we're seeing is a variable named scores, which is a list of integers, being assigned a list literal that has some integers in it, and notice that they're not sorted. 95, 96, those are in increasing order, but as soon as we get to 80, we see that it's out of place. Well, Python has a built-in function named sorted that's available without having to import it because it's a built-in. And what sorted does is you give it an argument, which is a reference to some list, and what it will return to you and what it gives back to you and what it will assign as part of this assignment statement back to sorted scores is a new list where the values of the original input list are in sorted order. And this is in ascending or least to greatest order by default. So what happens when we print sorted scores is we'll see that sorted scores is now a copy of our original list such that each of the items are sorted and scores is left unchanged, meaning that even though we gave this sorted function a reference to scores, which is a mutable data type, right? List is a mutable data type. Sorted could have reorganized the items within that original list, but this is a function that chooses not to mutate its input list. And in many ways that makes it easier to reason about than one that does, which we'll see in just a moment. So let's take a look at the results and convince ourselves that if we were to run this program, Python M lessons ls15 00 sorting, we see that our sorted scores are 60, 78, 80, 95, 96, 99. So they were correctly rearranged in a sorted order. Whereas the original input or the original scores list, which was our input to this sorted function, remained unchanged. It was not mutated. Now, there are sometimes cases where you would like to sort a list without creating a second list and having to keep track of it. Well, the list object and the list data type in Python has a built-in sort method that allows you to do that. It will mutate the original list. So let's try making an example of that in our code. So scores.sort. Now, one of the first things that you'll notice is this is a method call. So the list object and the list data type has a built-in method called sort, and it is a void or a function that returns none, a method that returns none. We think of these like procedures when they're plain old functions, but because this is a method, we just say that it's a method that returns none. It doesn't have any resulting value. What's happening is when we call sort on a list, it's mutating that list by rearranging or resorting the items in it such that they will now be in sorted order. And we could convince ourselves of this by printing scores out. And so notice that scores, when we printed it on line 8 here, was unsorted, but then when we printed that same list after calling the sort method on it, it had been mutated, its items were rearranged internally, and we have a sorted list. So this is one of the differences between an algorithm that treats its inputs as untouchable. It's not going to mutate them, which is what the sorted function does. And that means we're going to need to set up a new variable in order to work with its resulting values. And you might want to do this if, being sure that you kept track of the original ordering was important. For example, maybe you have a history of everyone who's played your game and their scores, and you want to keep that history in the order that people played them. But you would also like to be able to have a list of your top scores. you would probably want to have a separate list for that's sorted. Whereas sometimes you just want to rearrange the items of a list that you have without having to worry about creating another copy of that list, in which case using the sort method works. So how might an algorithm work behind the scenes? How might sorted or the sort method call work? Well, let's consider an example of this in a more conceptual sense, and then we will take a look at how we might implement this in actual code. So let's talk about insertion sort. Oops. Insertion sort is one of the oldest sorting algorithms there is, and it's nice to talk about in our class because it's pretty straightforward relative to some of the more advanced algorithms for sorting, which have some different characteristics. In many ways are improvements on this algorithm, but are harder to understand, and you'll learn more about in upper division computer science classes. So let's imagine a very simple list of numbers, like say 2, 3, 1, 4. So we've got a list with 4 values in it, and right off the bat, as humans, you can already see which of these items is out of place and what you would do to fix it, right? You would move 1 to the very front of your list somehow. Well, when we're working with a computer program, and algorithms more specifically, we've got to be very concrete and intentional about our way of processing a list. The computer can't just sort of infer and look at all these items like we can and know, okay, that one's out of place, so it's going to be shuffled around. We need a very deliberate set of steps. So let's think about one way that we might do this. And the intuition here, before we get into some of the more detail and then look at the actual code to implement this, is, if we think about the fundamental thing that we can do with any 2 items is swap them with one another. Let's imagine that we could swap 1 and 3 such that our resulting list is 2, 1, 3, 4. And then we could swap 1 with 2, which would give us 1, 2, 3, 4. This is the algorithm we're about to try and implement. And you might be wondering, why wouldn't you just, you kind of know that you can't really swap 1 and 2 directly, but imagine why can't you just insert 1 earlier on? Well, for reasons we'll see, we need to be able to think item by item in our list and break this down at a very simple basis of swapping 2 values. So we're shuffling this 1 back. So notice it's kind of moving back towards the position it should be in. So let's try and think about some of the components of what this algorithm might need to keep track of, or some of the state that it might need to be aware of. The first thing we want to consider is, let's imagine sort of this green arrow down, or this green caret is saying, hey, ignore everything that comes after this caret, right? So don't worry about these numbers. Let's try and think about this problem with a smaller scope. Let's try and figure out, is everything that comes before and including this green caret already sorted? One of the things that we can recognize right off the bat is when you only have 1 item in your list and you're only considering 1 item, it's sorted. There's nothing to rearrange. A single item list can't be unsorted, right? Just by definition. So this question becomes a little bit more interesting, and we'll assume that, if we have a single item list, our list is sorted, but let's start our problem by looking at the second item of our list, which is index 1, right? Because these indices, remember, are 0, 1, 2, and 3. And we'll come back and we'll think more about indices and the implications of working with an algorithm and its indices in just a moment. For now, let's keep this more conceptual. And so now we're trying to ask, okay, from this point back, from 3 and 2, is our list sorted? Is our list sorted is a sort of difficult question to answer. That's still a pretty high level question. But if we take for granted, or as a matter of fact, if we take it just as truth, that everything up until we got to the point of looking at this next item, we know that what came before it was sorted. So now the question is really just, is the current item that we're looking at, and remember we're ignoring everything after this caret, is the current item in the correct position? How can we know that? Well, we're going to have another thing that we're keeping track of, which is, okay, this is the item we're trying to place, right? So the item we're trying to place is the value at index 1. So when we move the caret forward, we're always saying this is the item we're trying to make sure is in the correct place. And what are we going to do? Well, we're going to compare that with the item that comes before it, right? So I'm going to circle that in pink. And 3, does 3 come after 2? Yes, that's correct. So we've completed this step. We know that, okay, up until the green caret here, everything is sorted and all is good. So I'm going to draw another iteration here, 2, 3, 1, 4, and move this caret forward, right? And so now we're going to ask the same question. We know that everything before this is sorted in the way that we want it, based on what we've said so far. Now the question is, what about this item? This is now the item that we're trying to make sure is in the correct place. So what do? Well, we compare it to the item that comes before it. And well, 1 is less than 3. So this is incorrectly sorted. And what do? Well, we need to swap these two values, all right? So we're going to swap these two values when we recognize that the current thing we're focused on is not in the right place. And we're going to move it back effectively by swapping it with the thing that came before it. So our new resulting list is going to be 2, 1, 3, 4. And we're going to keep this caret in the same place, right? This is sort of where, up until this point, we're saying this is where we're trying to sort our list that comes before this. But notice that the thing that we're focused on is still potentially not in the correct place. We need to keep asking the same question of, okay, well, is this item that we're trying to put into the correct place still, has it actually made it there yet? Did that swap finished? Is it now sorted? Or do we have more work to do? So once again, we're going to compare it with the item that came before it and see is 1 greater than 2? No, that's not true. So what do we need to do? Well, we need to swap these two values. So there will be another swap. And then we would have 1, 2, 3, and 4. Notice that our caret is still going to be on 3, but the item that we're currently focused on is now all the way down at index 0. It's moved to the very front of the list by swapping it back. And now, well, there's nowhere else for this item to go, right? There's no item that comes before it, so there's nothing, what comes before it can't be greater than what it is. So we're done, and this seems to be in the correct position. We're now ready to move our green arrow, which is saying, okay, now we've sorted everything that comes before the green arrow, and including the green arrow, and move it on to the next item. So next we would say, okay, 1, 2, 3, and 4. And we're now focused on this item. And we're going to say, okay, let's make sure that everything, including this item, is sorted in the correct place. So we look at this item and we ask, how is it? Is it in the correct place relative to what came before it? And the answer is yes. So we would move our caret 1 more and realize, well, we've now reached the end of our list. And by virtue of this caret indicating that once we move it forward, everything that came before it is now sorted, means that we've got a sorted list. Okay, so let's think a little bit about these 3 ideas. This caret is going to be the index we're focused on. So in the algorithm that we're about to look at, the implementation of it, I is going to be this caret, right? So I is this caret. And that means we're going to start I at 1. For the reasons that we mentioned before, we don't need to start our I, or where we're focused on making sure we've sorted everything before it, until 1, because the single element list is already sorted just by virtue of it having only 1 value. Then we're going to have this second concept that we need to keep track of, which is J. All right, so J is whenever we increase I, J is going to be what I is, but each time we swap this item back, we're going to need to subtract 1 from it, and we're going to need to move our index back. So notice that when we're swapping backwards, we're effectively moving the item that is out of place into its correct position, and that's what we're attempting to do. And then this last concept, this pink, is actually going to be just J minus 1, right? So if J is, so I is sort of our progress through the problem that we're solving. It's keeping track of where we are in the problem. and everything that comes before this is considered sorted. J then would be the current item index to correctly position. Right? And J minus 1 is going to be the index that comes before J, right? And that makes sense. It's just J minus 1. And we're always comparing, okay, relative to what comes before me, am I in the correct place? And if not, we're going to swap and then keep checking until this item is correctly placed. And this is an algorithm called insertion sort. So let's take a look at what this might actually look like in an implementation. First, before we look at the actual functions, let's consider our input. So notice we're using the exact same example as we just walked through, 2314. And I've defined a function named isort, short for insertion sort. And I would encourage you, if you'd like to follow along, to pause the video here and set up a file and try working through this algorithm with me, right? So insertion sort is a function that takes a reference to a list. And notice that this is a procedure. So this function is going to modify or mutate the reference that it's given. Meaning, we didn't have to assign the result of this function call to anything. We were changing nums. So by virtue of giving isort a reference to nums, we are in fact mutating that list, and we're changing the ordering of things in it if they are not sorted correctly. Okay, so as I mentioned in the previous example, I is our caret. So I is where we are, the progress. Right, through as we're moving through each index in our list and trying to be sure it's sorted. And notice we are starting it at 1 for the reasons as mentioned. J is going to be another variable we use, and J is going to be the current index we're trying to put in the correct place. So J is the circled item, current item index to correctly place. And by correctly place, I mean sort. You're trying to sort this item back to its position. This is a lot like when you have, a hand of cards and you realize you're trying to sort the cards that you're holding. You might move one back a few positions to be in the correct place. All right, and then we see here for the very first time a nested while loop. So what's going on here? Well, this first loop is saying while I is less than the length of x's, so while I is less than the length of our input list, what we're going to do is move through each I. So we're going to ignore this for just a moment. And notice that we're just saying, well, I is less than the length. Each time we do whatever we need to do for that given I, we're going to increase I to move forward by 1. What this is the code implementation of in the diagram we were just looking at is, remember I is this green arrow. So we're saying, okay, this is one step of I, the very first step where I is 1. And then the second time when we move I forward to the next index, which will be 2, we see that, oh, there's some work that needs to be done here. We actually have more things to do. This wasn't in the correct place. So this is going to be our second while loop. That is taking care of swapping 1 back, right? And then once we move on, once we complete this iteration and make sure that 1 is correctly in its sorted place, then we're going to move that cursor forward, or the progress arrow forward, the I variable to the last item, and that will be the last loop. Right? So let's take a look at this. And think about, okay, so I is what's moving our cursor forward. That must mean that this is what's actually moving or swapping back the incorrectly sorted values. So swapping back incorrect items. Okay, so let's take a look at what this is doing. Well, we're saying j is I. Right? So j, remember, is our blue circle. J represents the index of our blue circle. And if we once again just jump back to that, that means, as soon as we move on and we start considering, is the current item we're looking at, is it in the correct place? J is going to be that same index as the green arrow. Same with here, we move it forward, the green arrow, that's I, and J is, going to be referring to the same index as this blue circle. Okay, so J is going to, move forward along with the green cursor and say, okay, now our job is to be sure that the item stored at index J, which is the current thing we're trying to make sure is in the correct place, is less than the item that comes before it, right? Or I should say is greater than or equal to the item that comes before it. So notice we're only going to swap when it's out of place. And so this would indicate to us that these items are out of place. So let's think through this condition a little bit in more detail. So while J is greater than 0, remember, J refers to the index of our blue circle. So at this index, so notice J would have been 0 here, right? There's nowhere else for us to swap. We're saying J is now, the current item we're trying to put in the correct position is now at the very front of our list. There's nowhere else for it to go. Our work is done. We don't need to swap it back anymore, okay? So while J is greater than 0, that means it potentially needs to be swapped. And the second condition is saying, okay, well, let's just be sure that it needs to be swapped. This would be that it's out of place, right? So if it's out of place, that means that the current item is less than the item that came before it, right? So 1 is less than 3, that means we need to swap those two values. 1 is less than 2, that means we need to swap those two values. So what do we do inside of this while loop? Well, we swap, and we previously looked at the swap function, so I'm not going to cover that in more detail, but effectively we're saying, hey, swap this input list, swap the item at index J with the item at index J minus 1. So effectively swap the current thing we're trying to put in the correct place with what came before it. And then we are updating J to be 1 less than itself, right? So effectively, we're doing in 2 steps here. We're swapping the values of our list, which is like what we did between lines here. And then by subtracting 1 from J, we're saying, okay, the new index that we're focused on is the one that came just before the current item, or what it was previously, right? So in essence, we're moving the item back and we're keeping track of, okay, well, the new index of this item is now itself minus 1. The new index of this item is now what it was before, minus 1, until this condition is no longer true, right? So until we either have that item at the very start of our list, or it is now greater than or equal to the item that came before it, meaning it's in the correct position. And we know that because of what we call the invariant, that everything that came before us when we iterated in this loop would have been in the correct place. And so when this while condition becomes false, we know that we continue on and increase I. And that's what causes our cursor to go to the next item and continue that process again and again. To be a little bit more precise about what's going on inside of this inner loop, and because we haven't spent much time talking about the idea of nested loops, let's just consider one example of this. So let's try and recreate the state where we actually started swapping and things were out of place, right? So that would have been, what we're going to try and do is reproduce this state right here. So if we think about what is I in this state is going to be 2, right? So I is going to be 2, and J is also going to be 2. So let's jump back to VS Code and imagine, okay, our X's is a reference to a list of integers where we have, it was still in the original ordering, so that was 2, 3, 1, 4. At indices 0, 1, 2, 3. And then we have our I, which we said was at index 2, right? So referring to this one. And 2, so let's imagine we're right here. 2 less than the length of x's. Well, the length of x's is 4, so that's true. We go in. And now we're saying, okay, j is going to be whatever I is. So j is going to have a value of 2 as well. And now we ask, is j greater than 0? Yes, we're not at the very start of our list. We're at index 2, not index 0. So now we need to consider this. X is index j. X is index 2. Is that less than x's index 2 minus 1, which would be 1, right? So x's index 2 is the value 1. X's index 2 minus 1, or 1, would have been 3, right? So we're comparing 1 with the item that came before it, which was 3, and these are out of order, right? So this is true. 1 less than 3 is true. So what do? Well, we swap x's with these indices. Now, I'm not going to jump into this function and carry it out like we would on a true environment diagram, but what we know about swap is that it's going to say, okay, if I'm swapping j, which is 2, with 1, that has the effect of swapping these two values in the list, right? So now index 1 has a value of 1, and index 2 has a value of 3. Okay. And then inside of this loop, we need to subtract 1 from j. So j is now 1, right? And we go back to the top of the loop, and now we're asking, is j greater than 0? Well, j is 1, so that's true. And x is index j, so x is index 1. Is that less than the one that came before it, right? The item that came before it, which was 1 minus 1 is 0. Well, we look in our list, and we see that, okay, x's index 1 is 1. 1 less than 2 is true. So the item at index j is still out of place. That means what we're going to do is we're going to swap it. So swap the item at index j with what came before it, which would have the effect of moving 1 back before 2, just like we saw in our in the intuitive look at this. And what do? Well, now we decrease j by 1. So j is going to be 0. We go back up to the top and we see, well, j is greater than 0. Well, 0 is greater than 0 is false. And because this is an and condition, Python isn't even going to evaluate what comes after it. This is a sort of an optimization, but in this case, it's actually really handy, because if we did, we would ask what is the index of x is negative 1, which we don't really know how to interpret what that means yet. But because this is an and false and something is always going to be false, we're not even going to worry about this. We just know that this inner loop is done. And once that inner loop is done, we're able to continue on and say, okay, well, let's increase I by 1. So I is now 3. And that is the step. We move j back, swapping that item each time, 1 by 1. And then when we increase I by 1, we're saying, okay, move this cursor to the very next item in the list, and we're ready to begin that same process again. And if we were to keep carrying this out, what we would see is, well, j would also be updated just very briefly. Here, j would once again be updated to 3. And now j greater than 0 true, but we ask ourselves, is this item is 4 incorrectly ordered? So how do we know whether it's incorrectly ordered? Where we compare 4 less than what came before it, right? j minus 1 is the item that came before it, which was 3, and 4 less than 3 is false. So we know that that's correctly positioned, and we don't go into the while loop. We increase I by 1, so I would now be 4. And 4 less than 4, which is the length of our x's, is false, and this function would be done. So we've got a generic algorithm, and this is an implementation of the insertion sort algorithm for sorting any list of numbers or integers here. And we could convince ourselves that this still works by adding some additional items to it, like, -1, 10, 20, maybe a 5, maybe a 3, or a 2, 1, right? And if I were to run this program again, so Python lessons.ls15 one insertion sort. Notice that our resulting list has all of the original input items, but they've been resorted. And notice that this was done through mutations. We were actually mutating the reference that we gave to this isort function. So this behaves more like the list's built-in sort method than it does like the sorted function, right? If we wanted to, we could have implemented it more like the sorted function by making a copy of all of the values in the input list and then sorting those in the same way using this sort of mutation-based algorithm. So what's the big takeaway here? Well, there are a few things that are worth bringing home with you in this lesson. The first thing to realize is that sorting is effectively a solved problem. The reason why we look at implementations of sorting algorithms in computer science is because they're such fundamental embodiments of algorithms, and they have such important properties that we tend to teach those in much more depth in the courses that come after this one. And knowing how the various sorting algorithms work can help you decide which ones are appropriate for the applications that you're using and better understand just how algorithms work in general. Sorting algorithms are well defined, and there haven't been significant innovations in them in the past couple decades. This was a solved problem by the 80s, and there are better algorithms than the one we looked at. In fact, if you were to go look at the source code for how does Python's sorted function work, it wouldn't be the algorithm we used. That was much simpler than probably the quick sort or the heap sort or some other sorting algorithm that would have been used in Python's backend or its implementation. One of the key things to recognize about sorting algorithms is they kind of work in one of two ways. And we saw in the very first example a sorted function that didn't change. It did not mutate the list it was given. And that makes it pretty easy to reason about as long as you can remember, okay, I need to take whatever it returns back to me, which is going to be a reference to a new list of sorted values, and that's going to be my result. And that's different from an algorithm which mutates its list. And in which case, if you want to sort the items of a list without having to set up a new variable to keep track of it or remember that it's going to return to you a new reference to a new array or a new list, you can use the sort method, and that'll do that. The implementation that we looked at here was a fundamental, simple sorting algorithm called Insertion Sort that demonstrated how we might use two nested while loops in order to carry out a more advanced sequence of operations. We looked a little bit more intuitively at how this worked behind the scenes and what was going on in that algorithm. And whenever you're faced with an algorithm that, if you were to just look at this code, it would feel pretty opaque, these I's and these J's and what's going on. Well, trying to visualize what's happening with some actual data when you're tracing out an algorithm is a valuable practice to carry out. And this is an example of why you might use swaps. So sorting algorithms are fundamentally revolve around this idea of needing to be able to swap two items at various positions in a list until you get to a fully sorted list. That's a brief introduction to sorting in Python. And with this, you can now sort some data. Later, we'll look at how can we get these items in reverse order or descending order. And when we have more complex data that might have many properties, such as items in your shopping cart, you might want to sort by different properties, such as their price or their titles or their ratings and things like that. They're not much more difficult, but this is a good enough introduction to start being able to sort data in the programs that you're working with.